All right, so we did a little bit. If you go back to Friday, our primary focus was in concentrations. We were doing concentrations of solutions. We looked at things like percent by mass. We looked at things like percent by volume, mass volume percent, and then we ended with molarity. And all that kind of went hand in glove with what you were doing in lab with solution making that week. What I want to do is I want to rewind us. I want us to go back now to the first three parts of this chapter, which are considerably shorter, and kind of go into the fundamentals of what a solution is and how a solution forms. Now that we know kind of how to calculate those values. So let's start off with some baseline definitions. What is a solution? Well, by that logic, a solution is a homogeneous mixture of two or more substances, with each substance keeping its own chemical identity. Now, that particular definition should sound familiar to you. The reason why it should sound familiar to you is because it is the exact same definition that we used in chapter 1 to describe homogeneous mixtures. And that's because solutions are an example of homogeneous mixtures. And we can recognize them by their uniformity in appearance. They have the same composition, or excuse me, the same appearance throughout. But now that we have a little bit greater of an understanding of chemistry and of physical science overall, we can expand upon this. And so now we start to look at, well, what are the parts of a solution? And to answer that, we understand that every solution has at least two components. There is the solute, that is the substance that is dissolved, and the solvent, the stuff that dissolves all of the other stuff. Now, by definition, we would call the solvent that substance that is present in the greatest amount. More often than not, that particular substance is water. And so when water is the solvent, we call that solution an aqueous solution. Now, as has been said before, solute is the thing that is dissolved. So it is any part of the solution that is dissolved in the solvent. And a solution can have multiple solutes. So think of it from the standpoint of you're at home making Kool-Aid. Inside that Kool-Aid, not only do you have the water, but the Kool-Aid packet has flavoring in it, coloring in it, and you got to add sugar to make the Kool-Aid taste good. Well, all of those components, the coloring, the flavoring, and the sugar, all of those would be solutes in the overall solvent of water. So it is very possible, and in fact, most solutions have multiple solutes for that solvent. But we have to ask ourselves another question here. So we've taken the solution, we've comprised it, and we've broken it down into different parts, the solute and the solvent. But why does a solution form in the first place? What makes something soluble in water when other things are not soluble in water? And the answer here has to do with something called polarity. Now, in our previous work, going back to chapter 8, I believe, where we talked about bonding. We talked about the idea of bond polarity. That is, I have two atoms in the bond. The electronegativity difference between those two atoms is going to create this unevenness of sharing of those electrons and create a polar bond. Well, molecular polarity is kind of similar. Only instead of talking about one atom sharing electrons versus another, what we talk about instead is unevenness of sharing of electrons inside of a molecule. So take water, for example. Water is a polar molecule. Its structure is such that the electrons inside of that water molecule spend more of their time around the oxygen than they do around the hydrogens. And what we get as a result of that is we get a molecule that has some positive tendencies over here and some negative tendencies over here, and that's able to attract other positives and other negatives in other molecules. So why do polar molecules tend to attract each other? Why do they tend to dissolve in one another? Well, they've got these poles, these positive and negative ends that attract each other. Nonpolar substances don't have these poles. And as a result, they don't tend to attract to other molecules very well at all. They just kind of slide over each other. And if we get two different kinds of molecules together, they interact with each other in a very strong way. If I take a polar molecule and a nonpolar molecule and put them together, the polar molecules all seize up and tighten up next to each other and kind of push away all of the nonpolar molecules. What do we get as a result? Layers. The polar molecules all bind together. The nonpolar molecules all get kind of pushed out to the side. We end up getting layers as a result. This is known broadly as the like dissolves like rule of solubility. Substances with similar kinds of polarity dissolve in each other. So polar molecules dissolve in other polar molecules. Nonpolar molecules dissolve in other nonpolar molecules. But there's no crossover between them. Polar and nonpolar do not mix. And so when we start to look at things like alcohol and water, why do alcohol and water dissolve so well in each other? Well, they're both really polar. And so the positive ends of the water and the negative ends of the alcohol attract each other, and they end up dissolving well in each other. This is also why polar molecules like water tend to do really well with ionic compounds as well. Think about ionic compounds. They're charged as well. So the charges on the ions attract the charges in the polar molecules, and they dissolve in each other. We can quantify this relationship of solubility, how well something dissolves in something else, by measuring the solubility of that substance. And how we do that is we usually measure how many grams of a solute will dissolve in 100 grams of that solvent. That is the standard term for solubility. And so we can quantify just how soluble something is, or just how insoluble something is, using solubility characteristics like these. But what's interesting is that some substances, even though we would expect based upon their polarity to dissolve in one another, don't always do so. This is especially true for certain types of ionic compounds, where we know that an ionic compound should separate. An ionic compound should dissolve in water because of the ions in the ionic compound and the charges on the polar molecules of water. Yet this is not always the case. And so what we look for in these kinds of chaotic, disordered arrangements are patterns, things that can help us to kind of define when something is supposed to dissolve versus when it is not supposed to dissolve. And sometimes those are hard to find. Sometimes they're a little bit easier to find. In general, what they follow is a list of what we call solubility rules. And you can find a list of solubility rules on table 11.1 in your textbook. These are your solubility rules. Now, there's a lot in here, but they can basically be broken up into 3 categories. The first category, given by these top 2 lines, these ones always dissolve. Now you look at what's in there and you say, okay, I could see that. Sodium salts, potassium salts, ammonium salts, nitrate salts. It's not listed on here, but acetate salts tend to fall into this category as well. If I look at my ionic compound and I look at its chemical formula and I see one of those ions in it, you can rest assured that it is going to dissolve in water. There's a second category in here. This group is what we would call usually soluble. Sulfates tend to dissolve in water pretty easily. There are some exceptions on there: barium, strontium, lead, calcium, and so on. But for the most part, it's pretty reliable. Same thing with halide ions, chlorides, bromides, iodides. Most of those dissolve in water. In fact, the most common ionic compound that anyone can think of is sodium chloride. Most chloride salts dissolve in water. If you go into the lab, most of the stuff that we deal with that is soluble in water is either a sodium salt or a chloride salt or both. Why? Because these compounds tend to dissolve pretty easily in water. This last group these are usually insoluble compounds. So silver salts are usually insoluble. Oxides and hydroxides are usually insoluble. Sulfides are usually insoluble. Chromates, carbonates, phosphates, sulfites, silicates, usually insoluble. There are some exceptions. The exceptions primarily speak back to that first category: sodium salts, potassium salts, ammonium salts, and the like. Now, this is a pretty handy list. One thing I want you to think about, though, I want you to be aware of. You don't have to memorize this list. This is not something I'm going to require you to know how to do and be able to recall from memory. But what I do want you to be able to do is I want you to be able to look at this list and look at a chemical equation and say, okay, I've got barium sulfate and water. Will it dissolve? Well, I look at this and say, okay, most sulfates are soluble, but barium sulfate is one of the exceptions. It's not going to dissolve in the water. I want you to be able to rationalize things when they come up. And that's what this table is for. So you need to know how to use the table. You will be given the table in a testing situation, though. All right, any questions about the solubility rules table before we move on? All right, let's talk about another type of solution. This is called an electrolyte. Now, you got an exposure to electrolytes a couple of weeks ago in lab. You did that business with the light bulb lighting up in certain kinds of solutions, but not other kinds of solutions. Electrolytes, in general, are solutions that are capable of conducting electricity. And they conduct electricity due to free ions being in solution. So what I mean by that is in that solution, you have to have ions present. If the ions aren't in the solution will not conduct electricity. The more ions that are in the solution, the better it is at conducting electricity. And that brings us to the difference between these two terms. Our strong electrolytes, these are substances that have lots of ions in solution and are going to conduct electricity quite well. This usually comes from the idea of we've got some kind of ionic compound that when it dissolves in water, it breaks apart into ions, and it breaks apart into a lot of ions when it does. Weak electrolytes, on the other hand, they still conduct electricity, not nearly as well. And this comes primarily from what we would call a partial dissociation. Now, weak electrolytes tend to be molecular compounds that can break apart into ions. And so in particular, we are talking about things like weak acids and weak bases in this category. And the reason for their weak nature is because of their molecular character. Remember, molecular compounds, covalent compounds, are held together through the sharing of electrons. And that shared electron bond that exists between them has to be broken in order for them to be ionized. And a lot of times water is not capable of breaking that ion very easily, not capable of breaking that bond very easily. So that's really the big difference between strong electrolytes and weak electrolytes. Strong electrolytes tend to be ionic compounds that when we put them into water, they break apart and form the ions that make them up. Weak electrolytes tend to be molecular compounds that can break apart into ions, but we've got to have the right set of conditions. And usually when they do break apart, it's not nearly as successful. It's not nearly as prominent as the strong electrolyte, which is why it conducts electricity lesser. Non-electrolytes, on the other hand, these are substances that do not dissociate into ions. Primarily here we are talking about molecular compounds that will not break apart or pure gases, pure liquids, or pure solids. So these are substances that do not dissolve at all. So in the case of the pure gas, the pure liquid, the pure solid, it doesn't dissolve into the water. Or if it does, then it's a molecular compound and it's not going to break apart into ions. So those are the three different kinds of compounds that can form as electrolytes. Now, as mentioned before, electrolytes are capable of conducting electricity. How it does it is, well, as you saw in lab, this is the kind of setup that would allow this to happen. So I've got a light bulb that has two electrical leads that are separated from each other. When put into solution, those leads are stabilized by the positive and negative charges. So I've got positive ions and negative ions in each of these solutions. And so the electricity, the electrons are stabilized by these ions present in the solution, and that allows the electricity to go from one end to the other safely. And that is what completes the circuit and allows the light bulb to light. And so it doesn't matter what we are looking at. And so what we are looking at here is a case of I've got a strong acid in the form of hydrochloric acid and nitric acid. I have a strong base here in the form of sodium hydroxide. I have a ionic compound here in the form of sodium chloride. All three of those are very capable of conducting electricity and doing so very well as strong electrolytes. And we see this regardless. And so on their own, none of these compounds would actually conduct electricity. Sodium chloride, hydrogen chloride gas, sodium hydroxide solid, all of those, if I tried to do the same thing, put that electrical lead on them, they would not conduct electricity on their own. The reason why, those ionic charges are fixed in their spots. They aren't moving. Electricity requires the movement of charge, which they won't be able to do. But once I dissolve them in water, the water separates those ions from each other. And now we have mobile ions, which are capable of moving that electrical current from one area to the other. As I mentioned before, non-electrolytes tend to form out of molecular compounds. They do not break apart. So even in this scenario where I've got hydrogen peroxide in the liquid phase, when I dissolve it into water, you can see all of those atoms stay intact. I've got 2 hydrogens, 1 and 2, 2 oxygens, 1 and 2. They don't break apart from each other. They stay together. As a result, we get no ions. We get no electrical conductivity. When it comes to making solutions, there are 3 primary factors that we can look at to determine or impact how quickly a solution can form. Now, solutions will form on their own with no interference from us whatsoever. If I take a spoonful of sugar and just drop it into a cup of water, it will eventually dissolve on its own. It'll take a while, but it will eventually dissolve on its own. Now, if we wanted to hasten the process and make it go faster, there are some things that we could do. The first is we could impact the size of the particles of solute. This has everything to do with surface area. The more surface area that we introduce, the more quickly it will dissolve. So the finer the powder is, the more surface area it's going to have, the easier it's going to be to dissolve. This is why rock salt takes forever to dissolve, whereas fine salt dissolves almost instantaneously. Now, in some cases, that's a good thing. But if you're trying to make a solution quickly, it's not always the best case scenario. Another way that we can make solutions happen faster, we can stir them. Stirring them also introduces a concept of surface area because it's allowing the movement of those solvent particles around to attract and to come into contact with new surfaces on the solute to allow that dissolving to happen more quickly. I get higher degrees of interaction, which means I'm going to get higher rates of solution. The third factor overall, temperature. When I increase the temperature, that means that those water molecules are moving faster inside of that solution. Increased speed of motion is going to increase the number of interactions, which is going to cause the dissolving to occur faster as well. So those 3 factors, particle size, smaller particles, higher surface area is better. Agitation, stirring solutions will always cause them to dissolve faster than unstirred ones. And temperature, higher temperatures are going to make solutions faster than colder temperatures. Those are the 3 main factors that can determine how quickly we can make a solution. And so when we're making solutions, those are the things that we will look to manipulate whenever possible to try to make the solution forming process a little bit more reasonable. Again, think about the lab that you did last week. When you made that copper sulfate solution, some of you had big chunk copper sulfates. Some of you had more of a fine crystalline powder copper sulfate. At least in my lab, the people that had the chunks had to heat it a little bit longer, had to go a little bit longer to make that solution. Whereas if they had the other one, those people tend to be done faster. It dissolved a lot more quickly in that way. One note here about solution formation that we're going to talk about before we break for the day. The previous slide kind of hinted toward this. As a solution is made, those solute particles are going to be evenly distributed throughout the solution. Now, it doesn't always start that way. Solution formation always starts very locally at wherever the solid is. But given enough time, that solute is going to evenly distribute throughout the solution. And if you do things like heat it, stir it, that's going to happen all the faster. I mean, stirring it is the best way to get that even distribution because you're going to literally force those solute particles to move to other parts of the solution. But this is a really important note. Solutions really only tend to form when there is a greater level of attraction between the solute and the solvent compared to what the solute had by itself, what the solvent had by itself. This kind of speaks to those intermolecular, or excuse me, those speaks to those solubility rules. Why are certain ionic compounds insoluble, even though we would predict based on their polarity that they would be soluble? It has everything to do with what's holding that crystal together. In the case of barium sulfate is way more attracted to itself than the barium ions and the sulfate ions are attracted to water. And as a result, it stays as a solid. It doesn't break apart. It doesn't dissolve. Why don't oil and water mix? Well, we know it has to do with the polarity. But if we think about it from that perspective, the polar molecules of water are way more attracted to each other than they would be to the oil molecules that are nonpolar. And as a result, those polar molecules stick together, squeeze out all of the nonpolar molecules, and they end up forming layers. They end up separating. On Friday, we are going to talk about the last little bit here about solubility, looking at structure, temperature, and pressure. And then we're going to kick back to the end and talk about titrations and some calculations regarding acids and bases. That'll set us up very nicely for chapter 13, which will start next week. Have a good afternoon.